All right, so we're going to take a look at nonlinear functions. So let's first just break down the word nonlinear. We already talked about how a linear function was a graph whose points create a line, right? Whose inputs and outputs create a line. So going back, non means not. And so just to go back to those prefixes, so what we're talking about here is not a line, because we talked about how linear creates a line. So nonlinear creates, or is not a line. And so we're going to be talking about those nonlinear functions. We did have a glimpse of one of those in the beginning of 7.3, where it was a function, but it wasn't a line in that first example that we did. So we're going to talk about our key concept, what makes it to where we do not have a linear function, or where we have a non-linear function. So this table represents a juggler's ball being tossed. So if you just kind of think of a juggler tossing a ball, and if I had one nearby, I'd go ahead and toss it. Now, when we toss that ball up into the air, as the ball rises, its speed will decrease. Because, if we go a little sciencey here, because of the gravity working it back towards the earth and pulling it back down. So speed decreases. Now, as it falls, though, so as the ball falls, the speed will increase. Now, because both of these things are happening within the same function, as the ball goes up, it reaches its highest point and then it comes down. So as it goes up, its speed decreases, and then as it comes down, its speeds increase. That's not going to create one line when we are finding the speeds at certain, amount of time, so certain seconds. And so our rate of change is not going to be constant, and we can see that from this table. So from 0 seconds to 1 second is a difference of 1, right? And we're going to, from each of these, have, because we're just increasing by 1 second for each of those. But when I look at my height, from 0, I'm at a height of 3 feet. We must be starting off pretty low. So we have a height of 3 feet, and we're going to 5 feet after 1 second. So that's a difference of 2. But after, at 2 seconds, we only increase by 1 foot. And then at 3 seconds, we start going down, and we're decreasing by 1 foot. And then at 4 seconds, we've decreased by 2 feet. And so we don't have that constant rate of change. And so as we put it on a graph, it looks something similar to this. It is still a function, because if we look at it and I put in those vertical lines, right, and I pass my pencil across it, or however I want to look at it, I'm only crossing this graph each time I draw that vertical line once. So it's still a function, it's just not linear. And so since the rate of change, there it is, since our rate of change is not constant, this is a non-linear function. And again, I know it's a function because for every input, I have exactly one output. Now, I know my outputs, some of my outputs show up more than once, but remember, it only matters that I have multiple x values per my y value. So as long as I only have one y value for each x value, all is good. So my rate of change is not constant, and therefore this is a nonlinear function. So now, identify whether each graph is a linear function or a nonlinear function. Well, that's pretty simple because all I have to do is look at it. So when I look at A, well that's a line, so this is linear. When I look at B, it's a definite curve. So this is going to be a, oops, that looks more like a W than an N. So this is a non-linear function. And then when we look at C, I know these are created by lines, but when we think of a line, all of them are going in the same direction. And so since these have what we call a vertex, this point right here, and then it goes down in two directions, this is still a non-linear because it makes a V shape. It may be created from two lines, but they're not each going off in both directions. Remember, a line goes for infinity in both directions. So that's how easy some of your homework is look at the graph. Is it linear? Is it not linear? So we have two nonlinears and a linear here. So example 2. Identify the tables that represent nonlinear functions and explain. So we're going to look at this first table. And I'm going to look at my input, and I notice that we're increasing by 1. So from 3 to 4 is a difference of 1, and from 4 to 5 is a difference of 1. So again, my input, my x values are looking good. Now when I look at my output, from -8 to -16, we're decreasing by 8. From -16 to -24, we're decreasing by another 8. -24 to -32, decreasing by another 8, and -32 to a -40, decreasing by another 8. And so because all of these are the exact same, that means that this is constant. So I have a rate of change. So since we have a rate of change that is a -8/1, which is a slope of -8, that makes this a linear function. So this is a linear function, and it's because we have, nope, I don't want you, a constant rate of change. And so if I have a constant rate of change, then we have a linear function. All right, so now looking at this next one, again, from 1 to 2, we increase by 1. From 2 to 3, we increase by 1. From 3 to 4, we increase by 1. From 4 to 5, we increase by 1. And when I look over here, from 1.5 to 2.5, we're increasing by 1. 2.5 to 5.5, we've increased by 3. 5.5 to 8.5, we've increased by 3. And 8.5 to 10.5, we've increased by 2. So when I'm looking, even though my inputs are the same, my outputs are not the same. Therefore, this is a non-linear function. And I know it's a function because each input has exactly one output. And it is nonlinear because our rate of change is not constant. Because our rate of change is not constant, that makes it a nonlinear function. So now on to our third one. So from 1 to 2, again that's 1, 2 to 3, a change of 1, 3 to 4, a change of 1, 4 to 5, a change of 1. And then 1 to 3, we increase by 2, 3 to 6, we're increasing by 3, 6 to 10, we're increasing by 4, and 10 to 15, we've increased by 5. So again, looking at this, we are not a linear function because our rates of change are different, because here I have 2/1, 3/1, 4/1, 5/1. So this will be a nonlinear function. Again, because the rate of change is not constant. So if my rate of change is constant, then we have a linear function. If my rate of change is not constant, then it's a nonlinear function, and that's how simple it is to tell the difference. All right, our last example for 7.4, example 3. So suppose there are 20 rabbits on an island and that the rabbit population can triple every 6 months. So we're going to make a table of values of how many rabbits there would be after 2 years. So that's our first step. So I'm going to make the best table I can make over here. And so we're going to have our time in months and our number of rabbits. And so we have to start off with 0 because after no months, we start off with 20 rabbits. And then it's every 6 months. And I said months, but really I want time in years. So after 0 years, we have 20 rabbits, and then we're just going to go by halves. So after half a year, 6 months, then I'm going to take 20 times 3, and when I take 20 times 3, we end up with 60. So 20 times 3 equals 60. But it's wanting after 2 years, so I'm going to keep going. So after 1 year, then we would take 60, because every 6 months it triples. So I begin with the 60 and take that times 3, and so then 60 times 3 is 180. And then at 1.5 months, we're going to be at 180 times 3, which will give us 360. And then, nope, not 360. I was looking at the wrong number. We would be at 540. That makes more sense. And then at 2 years, we're going to be whatever 540 times 3 is, which is 1620. All right, so we've made our table of values to find out how many rabbits there would be after 2 years. So after 2 years, there is 1,620 rabbits. Now, be asked, does this relationship represent a nonlinear function? And explain. And so, again, our time, we're increasing by half each time. So our time is constant. We just have to look at our y values. And so 60 minus 20 is 40, but 180 minus 60 is 120. And so right then and there, I know that this is not a constant rate of change. And so the answer is yes. And it's because the rate of change is not constant. Excuse me. All right, now it wants us to use the table and then decide when we would expect the rabbit population to reach 1 million rabbits. So we just have to keep working, plugging along. So at 2, I'm going to start doing 0.5 instead of half. So at 2.5, we're going to do 1620 times 3, which gives us 4,860. And after 3 years, we're going to then take the 4,860 times 3 and get 14,580. And I'm going to finish out this table because I'm almost out of recording. So if you want to pause your video now so you can finish out your table while before I continue talking, that's okay. But I finished the table and it took 5 years, because after 5 years we reached the 1 million mark at 1,180,980. And so we can expect it after 5 years to reach the 1 million mark. And so again, it was just increasing the table and doing it times 3 each time. Unfortunately, there's not an easy formula for that. So That is it.